So we have discussed random graph model, we have discussed regular ring lattice model, we have also discussed Watt-Stockert model, right? And the property that we have not seen so far is the power law degree distribution, right? So today we will discuss the new model, which is perhaps one of the seminal models in the area of network growth, and this was proposed by Albert Barabasi and Rekha, Rekha Albert, and this is basically called Barabasi Albert model or BA model. Okay, so BA model is the first model which explains the power law degree distribution of a network. Okay, and this is more realistic. Reason is that if you think of the other models that we have discussed so far, okay, all those models assume that the number of nodes is fixed, okay, and number of nodes are given beforehand. You are basically designing mechanisms to rewire or to connect nodes in different ways, right? In case of random graph model, we connect nodes randomly. In case of Watt-Stockert model, we basically rewire the regular lattice, right, in such a way that after certain rewiring we'll get a small world network and so on. Barabasi-Albert model is a model which basically says that let the node come one by one, let the node join the system one by one with certain edges, and let the node decide which other nodes it wants to get connected. Okay, so this is also called preferential attachment model. Why it is called preferential attachment model? Because when a node comes in, right, let's say you already have this kind of network at time t, okay, at time t plus 1 a new node comes in with certain edges, right? So how does this node choose an existing nodes? How does this node choose other existing nodes for the connections, right? So the node will choose based on the degree, based on the current degree of the other nodes. So it means that the other nodes which are already there in the system, the other nodes will acquire a new edge. The probability of acquiring a new edge is proportional to the degree, to its current degree. Okay, so let's say there are two nodes. The node 1 has degree 10 and node 2 has degree 1. So the likelihood that node 1 will receive an edge is higher than node 2 receiving an edge. This is proportional to the degree of nodes at current point in time. So this is based on the preference with respect to the degree of nodes in a network, right? So therefore this is called preferential attachment model. This is also called rich gets richer model, and the reason is simple. You are basically allowing yourself to be connected to a node which is already rich, right? Rich in terms of degree, right? The node has already higher degree, and you basically give preference to those nodes which have already got higher degree. This is also called rich gets richer model. Okay, we will see that this rich gets richer model will allow you to generate a network which follows power law, scale free network, and this is also called scale free network, by the way. This Barabasi-Albert model is also called scale free model, scale free network, right? We will also see that this will allow you to generate hubs, right, or outliers. Now real world networks, real world networks always exhibit this kind of outliers or hub nodes, right, with a lot of degree, with very high degree. Okay, we will see that using these models you will also get nodes with higher degrees. Okay, so let's get started. Let me not use my slides. Let me use the whiteboard and derive things gradually, slowly. So this is little bit mathematically heavy, so you just need to follow whatever I am explaining here, right? So the probability that new node, the probability that a new edge, right, attaches to an existing node with degree di is P of di, which is, as I mentioned, this is based on the current degree, this is di, and we normalize, because this is probability, we normalize it by j, right? So by all the degrees, okay, and this is called preferential attachment. So let's try to understand the system first. So what is happening? So initially, let's assume that you have m number, you have m0 number of nodes in the system, because you have to start from some nodes, right? So let's assume that you have m0 number of nodes, and you also have roughly you have roughly m0 number of edges. Okay, roughly m0 number of nodes and number of edges is more or less same. It doesn't matter, right? You can assume that there is no edge, but if you assume there is no edge, then it would be difficult to calculate this probability, because nodes will have degree 0. So let us assume that on an average a node is connected to only one other node in the system. So roughly m0 number of nodes, roughly m0 number of edges. So you start with this setting, okay? Now a new node comes in with degree m. So this is a drawbacks, but let's assume that each node is coming with the same degree. The degree is same, which is m. Okay. Now each of these m edges will choose an existing node based on this preferential attachment, right? So this edge will choose a node based on the preferential attachment. Remember one thing, this is a probability, meaning that it is not always the case that always you will choose a node with high degree, right? With high probability you choose a node with high degree, but also there is non-negligible probability based by which you basically choose a node with low degree. Otherwise low degree will never grow, right? So this is a probability, okay? It's a probabilistic model. So this is the setting. So we basically need to determine when these nodes are coming in, and remember at every time only one node is coming in, only one node joins. So at time 1 one node joins, at time 2 another node with m edges joins, at time 3 another node with m edges joins, and so on and so forth, right? So we'll see that over the time t many nodes will join, right? m into t number of edges will join, right? We will see how joining of these nodes will change the degree, average degree. We'll see how the joining of these nodes will change the degree distribution, okay? So this P of di is di by sum of degree, right? Now sum of degree is what? Sum of degree is 2 into number of edges. So how many edges are there? So we have, so at time t, mt number of edges will be joined, mt number of edges have already joined, right? And if you just ignore the last node, because at time t you are calculating the number of edges, right? You will not consider the node. Let us assume that you are not considering the node which is joining at time t. So how many number of edges are there? You can roughly say that, okay, this is 2mt minus m. It doesn't matter, because this m is, and as t tends to infinity, you will say that this doesn't matter, so you'll have only 2mt. So 2 into number of edges. So this would be 2mt, right? So this preferential attachment is now di by 2mt, right? So now we will see, now this is degree, this is the probability of a particular degree di. We will see that how this degree changes over time, and how we can see that this P of d is actually proportional to di. P of di is proportional to di to the power some minus gamma, right? Because this is power law. We have to prove this. Okay, we will prove this thing. Okay, in order to prove this, we will use a theorem. So this degree dynamics is generally measured in two ways. So there are two ways to measure it. One is called continuum theorem, or continuum approach, and the other is called master equation. Okay, so using these two approaches, we will prove separately that the degree distribution follows power law. Okay, so let's start with continuum theorem, continuum approach. Okay, so we basically show that how the change in degree di, how the change in degree di of node vi gets affected every time as a new node joins. So this is something that we are trying to understand. Okay, so the new edge, right, or the new link, right, that gets connected to a node, right, is proportional to this one. So at time step t, right, we know that for the ith node vi, the probability of getting connection is p di, which is di by 2mt, right. So what is the rate of change of degree? So the rate of change of degree is delta di dt. Rate of change of degree di, think about it, rate of change of degree di when m edges are coming in. So this is basically m times speed di, because m number of edges are coming in, right. So and each edge will join a node with degree di is p di. So what is the change of degree di? Is m times p of di, right. This is basically m times di 2mt, which is di by 2t. Okay, so what we do, we basically take the integration. So d or del di del t 2t, right. We'll take the integral, because ultimately our task is to understand dit, right. So we take the integral from di ti to dit, right. I'm explaining what is this, what are these notations, tit and t, right. So ti is the time when node vi, right, when node vi, whose degree is di, joined the network. Okay, and t is something which is the current time. So these two things are clear. What is diti? Diti, what is diti? Diti is the degree of is the degree di at time ti, right. And what is dit? dit is the degree di at time t, right? So if we do this integral, you will get log of dit by di ti half log of t by ti. Okay, and if you do some modifications, you move half here and remove log in both the sides, so you will get dit by diti equals to t by ti to the power half, okay, which is basically dit, right, equals to diti times t by ti to the power beta. And what is beta? Beta is half in our case, right? And beta is called dynamical exponent. So this is the equation, right? Degree of Vi at time t is degree at time ti, degree of Vi at time ti times this one. Okay, so let's try to understand what is this. Degree of a node Vi at time ti. So what is time ti? Time ti is the time when node Vi joined. And when node Vi joined with m edges. The degree was m. So this is m. Okay. So we have dit is m times t by ti to the power beta. Right. This is very important equation. It's a very, very important equation. Try to understand. So there are three observations that we can draw. Number one is that dit is proportional to t to the power beta, right? This is also power law, which basically says that the growth, right, that the degree growth of node Vi is proportional to the time, right? Number two is called first mover advantage. What is first mover advantage? So you see that dit is inversely proportional to 1 by ti to the power beta. What is ti? Ti is the joining of node Vi. So it means that as ti, if ti is low, dit would be high. Meaning that if the node joined earlier, ti would be low and degree di would be higher. If the node joined earlier, it is likely that the node will gain a lot of degree. So the node which actually joined earlier, which joined first, will have advantage in terms of degree, growth. So therefore this is called first mover advantage. Okay, this first mover advantage is very important in the context of research, right? I mean, there are papers actually, which are not that scientifically concrete, right, scientifically fundamental, but those papers actually started a particular field or a particular research area. A simple idea, but since those papers started a research area, they actually got a lot of citations. Okay. The third one is called is future rate of change. Right? We basically try to understand that the rate of change of this degree. So this is degree at time t, and how this rate will change. So we need to take the derivative. So we'll take the derivative with respect to time. So del dt del t is, if we take the derivative here, assuming beta equals to half, so we will have half right? And m is diti, right? So half diti, right, by ti t to the power half, okay, which is basically proportional to 1 by ti times t to the power half, or root over square root of this one. So this is the rate of change. What does it mean? So it means that since the rate of acquiring new nodes is inversely proportional, rate of acquiring new nodes, meaning rate of change of degree, is inversely proportional to the current timestamp, the rate of acquiring of new edges by a node slows down with the time. So as time increases, this will slow down. Okay, so the rate with which a node, is supposed to gain edges is much higher at the initial level, and as the time increases, it will slow down. Okay, it is inversely proportional to t. It is also inversely proportional to ti. Okay, so these are three observations that one can draw, but the important thing to note is this equation. Okay, we are not yet done. We have to prove that the degree distribution follows power law, right? So let me erase this part. Okay, let me erase this part and let me use this region of my notepad, right? All right, so now what we will derive, we'll basically, so let me just recap some of the things. So at every timestamp t, there are at a particular timestamp t, how many nodes are there? There are m0 is the number of nodes at the beginning plus t, because at every time you have one edge, one node. So m0 plus t number of nodes are there, and how many edges? mt number of edges are there, right? Of course mt plus m0, but you can ignore m0. Okay. Also we need to remember that dit is what? This is the degree of node vi at time t. Okay. So let us denote a probability p, which is this one. So it basically says that the probability that that a randomly chosen node vi has degree less than k at t. This is important, right? So if you just think of this quantity, this is dit less than k, right? And we already know that dit is this one. So this is basically, I replace dit by m times t by ti to the power half less than k. If you do the math, you will get ti greater than, right, m by k square times t. Okay, so I can replace this by this. So this is same as, this probability is same as p ti greater than m by k square t, right? This is same as 1 minus p of ti less than equals to m by k square times t. Okay, now what is this one? This is basically saying that what is the probability that the time is less than equals to this one. Now time ti is same as number of nodes joining in, right? So at every time we have, now if you think of this pti, what is pti? Probability of a particular time ti, and this is uniform, always 1 by n. if n is the total number of nodes that we can expect at the end, right? Because at every time we have one node joining in. So this is a uniform distribution, right? And this is cumulative, right? This is basically cumulative. So at every time this many, so you want to measure the total till this part. So this would be 1 minus 1 by n times m by k square into t. Right? What is n? N is the total number of nodes. And how many total number of nodes are there? We already know the total number of nodes is m0 plus t. Right? I replace n by this one. Okay. So this probability P of di t less than k is this one. Right? And this is cumulative. So how do we get the probability density? We take the derivative. So this is cumulative. If you want to get the non-cumulative, we need to take the derivative. So then P of k, right, is essentially dk of P of dit less than k, right? Meaning we take the derivative of this with respect to k. If we do that, we will get 2 m square t by k cube m0 plus t. Okay. So what we get? We get pk, which is something that we wanted to measure, pdi, right? This is 2 m square by t by k cube m0 plus t. If t tends to infinity, what would happen? And if t tends to infinity, m0 can be negligible, right? This will vanish, this t and this t will vanish. So we will have pk 2 m square by k3, k to the power 3. What is m? M is the degree of a node, which is, the degree of a newly joined node. This is fixed. So m is fixed. So this part is constant. So we will have pk proportional to k to the power minus 3. Right? So the degree, the probability of a degree of degree k is k to the power minus 3, which is basically power law, where the coefficient also ranges between 2 to 3. Right? So this is the master equation. This is the continuum approach. Using continuum approach, you can prove that the degree distribution follows power law. So in the next lecture, we will continue with this, and we will also show the same thing, the same conclusion, by using master equation. Now, why I am explaining these two approaches separately? Because say you want to propose your own model. Using this continuum approach and master equation, you can also show that your model also follows the power law property. Okay. So in the next lecture, we will discuss master equation. Thanks.